Let's dive right in. If you've spent any time on X or LinkedIn lately, you've probably seen the phrase loop engineering popping up everywhere. And look, I totally get it. When a term spreads that fast, it's easy to dismiss it as just another tech buzzword. But I promise you, it's absolutely not. Loop engineering is the mandatory technical standard for building AI that can actually survive real-world traffic in 2026. If you want to move past those flashy, brittle demos and build an AI agent that doesn't just immediately collapse the second something goes wrong, this is exactly the explainer you need. Here is a quick look at our agenda for this explainer. First, we'll cover the 3 AI eras. Second, anatomy of the loop. Third, the deterministic system harness. Fourth, surviving context rot. Fifth, verification and human limits. And finally, we'll wrap up with the MINT framework. Let's get to it. Section 1. The 3 AI eras. The evolutionary zoom out. To truly grasp why loop engineering is so critical right now, we kind of have to zoom out and look at how we got here. The evolution of AI development is really defined by 3 distinct eras, each representing a shift in where the primary bottleneck of AI performance actually lives. A few years ago, the bottleneck was the prompt. Prompt engineering was the highest leveraged skill out there. Because early models were super rigid, the exact wording and phrasing of an instruction carried all the weight. Your main job was handwriting the exact input, because even a minor change in language could wildly alter the output. Then, as models got better, the bottleneck shifted to context engineering. Phrasing started to matter a lot less than curating the information landing in the model's context window. The job became assembling inputs, retrieve documents, conversation history, tool results, so the model had the right data to actually reason. But today, in the current era of agentic AI, we've moved to loop engineering. Modern models can basically write their own prompts and pull their own context via tool calls. So your role has totally shifted from designing inputs to designing the actual system architecture itself. Section 2. Anatomy of the loop, the AI customer support agent. Let's make these abstract concepts a bit more concrete by thinking about an AI customer support agent handling orders and refunds. The absolutely crucial thing to understand here is that a production agent is not a single-point reply generator. It operates in a continuous cycle. Let's say a message comes in asking for a refund. Step 1, the model acts by classifying that intent. Step 2, it realizes it needs more details, so it observes by calling an order lookup tool, and then it appends that record back into its context. Step 3, it verifies that data against the company's refund policy, and Step 4, it either retries if it's missing something, or it drafts and sends the reply. If you're familiar with the REACT pattern, reason, act, observe, and repeat, this is exactly that. Every single iteration feeds directly into the next one. But you might be wondering, what happens when we don't tell the loop to stop? Well, you get runaway loops. You have to explicitly engineer termination signals, or what we call stopping conditions. If you don't, the agent will just endlessly call tools, endlessly re-reason, and literally spin out of control on a task it can't even complete. And remember, every single iteration is a full model call. That means your latency and your costs are scaling directly with the length of the loop. So you absolutely need a clear done signal, a hard cap on iterations, a strict cost or token budget, or a passing automated verifier to just kill the loop before it completely torches your API budget. Section 3. The deterministic system harness, the unseen scaffolding. There is this massive, kind of funny irony in modern AI development. To make all this unpredictable, non-deterministic AI magic work, you actually need heavy, boring, traditional software engineering. We call this harness engineering. People get so hyped about the creativity of the model that they completely forget an agent is mostly just standard software underneath. The harness is all that deterministic code wrapped securely around the model. We're talking retry logic when a tool inevitably fails, timeouts when your database is dragging, and the guardrails that physically stop an agent from promising a refund it isn't authorized to give. Think about it. If your intent classifier is absolutely flawless, but your order lookup tool times out and crashes the whole loop because you didn't write fallback logic, that flawless classifier is completely useless. I love this quote from the source material. The model might just be 5% of the magic. The harness is most of whether this thing survives contact with real traffic. It hits the nail on the head. You literally cannot just evaluate a single isolated completion and say, hey, this reply sounds pretty good. You have to evaluate the entire system under stress. What does the system actually do when an API goes down, or when a customer gets super angry? That unseen scaffolding is what loop engineering is really all about. Section 4. Surviving context rot, the entropy of long loops. Now, we need to talk about a hidden killer that catches development teams off guard pretty much every single time. As your loop iterates during these complex, long-running tasks, The context keeps accumulating. Every tool result, every little reasoning step gets jammed into the context window. And the danger isn't just hitting a hard token limit, it's that you hit a quality wall way before that. We call this context rot. It's the measurable degradation of model quality when that window just fills up with stale, low-signal junk data over multiple steps. It's the exact reason why agents often start out incredibly strong and then just completely lose the plot halfway through a task. You have to start treating context as a scarce resource that you actively, ruthlessly budget. So, how do we actually survive context rot? Well, here are a few actionable techniques to filter that accumulating history. First up is compaction. This means periodically summarizing or compressing earlier steps so the model keeps the main thread without dragging around every single raw token. Second is external memory. This is writing facts out to a separate store and only retrieving exactly what's needed for the current step. Third is tool result management. Look, if a database query returns 1,000 rows, you do not just dump that raw text back into the model. You have to filter and extract it first. And finally, multi-agent orchestration. This one's a real game changer. Spinning off a sub-agent to handle a specific task with a clean, narrowly scoped context is actually a context management strategy, not just a way to flex your capabilities. Section 5. Verification and human limits. The golden rule of automation. When you're designing these loops, you really have to base them around a fundamental asymmetry in verification. Basically, what determines where automation ends and human review begins? Well, you have cheap, automated verification, things like, does this block of code compile? Or is this requested refund under $100 according to our strict policy? You want to bake those automated verifiers directly into the loop. Catch the mistakes early so the agent can retry on its own before the user ever sees it. But then you have expensive, subjective verification, trying to judge if an apology was polite enough, or handling a really sensitive, complex negotiation. There is no cheap way to automate that. So whenever the judgment is genuinely subjective or expensive, that is exactly when you escalate the loop out to a human. Section 6. The MINT Framework. Minimal Intelligence Necessary Tools. Okay, so how do we actually build all this crazy architecture without causing a total system collapse on day one? Enter the MINT framework, which stands for Minimal Intelligence Necessary Tools. The whole philosophy here is to build incrementally. Only add complexity when there is an observable bottleneck. Let's walk through it. Step 1, just get a basic prompt and workflow running end to end. Make sure it can answer a simple message. Step 2, add specific tool use, like an order lookup, to stop it from hallucinating. Step 3, add continuous system evaluation so you can actually measure if your changes are working. Step 4, add state and memory to remember past tickets. And step 5, only at the very end, when there is a proven, demonstrated need, do you add multi-agent handoffs. I promise you, the opposite approach, wiring up 5 agents, a massive vector database, and long-term memory before you even confirm the basic loop works, will completely kill your project. As we zoom out to look at the macro view of building software this way, we can look at Andrew Jang's brilliant concept of the 3 nested loops. Loop 1 is the agentic coding loop. This runs in seconds to minutes, and it's completely run by the agent testing its own code. Loop 2 is the developer feedback loop. That runs in minutes to hours, and it's run by you as you steer the specs and check the work. And Loop 3 is the external feedback loop. That one runs in hours to weeks, driven entirely by real customers interacting with your live system. What this clearly shows is that humans absolutely do not disappear in 2026 AI engineering. We just move to the outer loops where we have a strategic advantage in context and judgment. So I want to leave you with a final, slightly provocative question. Take a hard look at your current AI projects. Are you truly engineering an AI agent with robust stopping conditions, solid system harnesses, and active context management? Or are you just endlessly polishing a prompt while the underlying system collapses under the weight of real-world traffic? It's time to master the loop. Thanks so much for joining me on this explainer, and I really hope this changes how you build going forward.